Hello, my name is Yang, Postdoctoral Research Associate at the Center for Compressor Technology at City St George's University of London. Welcome to this week's Lecture Tuesday. Today we will be talking about the rotor profile design of twin-screw vacuum pump. In my previous lecture, I introduced the various rotor profiles, as shown on this slide. The design of rotor profiles play a critical role in determining the efficiency and the performance of twin-screw vacuum pumps. These profiles differ from those used in twin-screw compressors and typically feature one or two loops. The rotor profile curve is specifically designed to enhance the volumetric flow rate and minimize the leakage. In today's lecture, I will guide you step by step through the process of designing a rotor profile. The first step in rotor profile design is to establish and understand the coordinate systems. Three fixed coordinate systems, x1, o1, y1, x2, o2, y2, and x3, o3, y3 are defined for the main rotor, gate rotor, and rack respectively. Additionally, two local coordinate systems, x01, y01, and x02, y02, rotate along with the main rotor and gate rotor fixed coordinate systems individually. A third local coordinate system, x03, y03, undergoes translation. The center distance between the main and gate coordinate system is denoted as AC. As the main rotor rotates through an angle θ1, the gate rotor rotates through an angle θ2, where θ2 equals Z2 over Z1 times θ1. Here, Z1 and Z2 represent the number of loops on the main and gate rotors respectively. The rotor profile curve can be transformed and analyzed within these coordinate systems. The second step involves defining the generating curve and performing coordinate transformations to derive the generated curve. This profile can be specified on the main rotor, gate rotor, or on both. Alternatively, the primary profile can be defined as a rack. In the transverse plane, two types of transformations are typically applied: translation and rotation. Since the two rotors rotate in opposite directions, one clockwise and the other counterclockwise, specific rotational metrics are used for these transformations. For instance, if R1 represents the generating curve, R2 can be derived through a series of transformations. So first, rotation. Transform R1 from the local coordinate system x01, y01 to the fixed system x1, o1, y1. Second is the translation. Shift the curve to the fixed system x2, o2, y2, accounting for the center distance between the two rotors. Third is the rotation. Transform R2 from the fixed system x2, o2, y2 to the local systems x02, y02, which rotates with the gate rotor. This process, illustrated in the final equation on the slide, ensures that the generated curve maintains proper alignment and functionality within the two-rotor system. The last step is to calculate the meshing angle. The envelope method is used here as a basis for calculating meshing angle. The envelope method states that two surfaces are in mesh if each surface can generate or envelope the other through a defined relative motion as shown in last slide. The envelope method is also used as a basis for the generating of the rotor manufacturing tools. The cross product in the envelope equation represents a surface normal, and the partial R2 over θ2 is the relative sliding velocity of two single points on the surfaces 1 and 2, which together form the common tangential point of contact of these two surfaces. The meshing condition can be solved by a numerical method. Once getting the meshing angle, the meshing profile equations of the gate rotor in the transverse plane can be calculated according to equations. This slide illustrates an example of rotor profile design using a rack generation procedure. A rack represents a rotor with an infinite radius. The meshing condition theta can be directly solved without requiring a numerical approach. The generating curves consist of three straight lines defined in the Rex coordinate system. The generated rotor profile can then be calculated using equation 4, with the meshing angle theta determined directly based on the meshing condition. It is important to note that epitrochoid curves can't be defined on the rack and must be specified separately. By following this procedure, a Queen-Bee twin-screw vacuum pump rotor profile can be successfully generated. Thank you for listening. With that, we conclude today's lecture. For any further discussion and questions, please get in touch.